It's okay? Okay, so we can start. That's the farewell kind of lecture. So, good morning, everybody. Thanks for being still here. And today, it's a sort of wrap-up. I'm going to bring together several of the concepts that we have been talking about this week, hopefully with some connection to a real case, something that is still an open research topic, to give you an idea of how people think in this field and what can be typical open problems you might work on in the near future. And today I'm going to talk about multi-messenger aspects. Actually, yesterday in the exercise class, you already saw, in principle, a couple of examples of what people call multi-wavelength analysis and multi-messenger analysis. Multi-wavelength analysis was the case of the supernova remnant photon spectrum, and you saw that, you know, this funny double bump shape, so you measure photons at different wavelength, and you use this synoptic type of information to infer things like the intensity of the magnetic field or the properties of the underlying electron spectrum producing this type of signal. And you also saw, in a very loose sense, what people talk about when they talk about multi-messenger, the case of fragile elements, secondaries over primaries. You combine information from spectra of boron with spectra of carbon, and their ratio is telling you something about propagation properties that you can use to predict the secondary antiproton spectrum. Okay, so you link different messengers, and by linking them together, you can be predictive, and you can try to study, for instance, dark matter through indirect dark matter searches. Today we are going to extend this approach to what is more properly thought about as multi-messenger. Usually people tend to talk about multi-messenger where you really combine different type of particles. In particular, today I'm going to show you some links among photons and neutrinos, and to some extent also with the protons or hadrons that are underlying their production. And the final application of this will be some consideration on the nature of the diffuse neutrino flux that has been, of astrophysical nature, that has been discovered roughly a decade ago now by the IceCube telescope at the South Pole. Now, you might not be familiar. How many of you know what IceCube is, how it works? Less than one-fourth, maybe, or something like that. Okay, so so just for you not to get completely lost, what has this telescope done, and actually what do we mean by a neutrino telescope at these energies? So a very quick introduction. This telescope of high-energy neutrinos work based on the detection of Cherenkov light. Okay, this Cherenkov light is produced when neutrinos. Think of a muon neutrino. A muon neutrino, which is very energetic. We are talking about TeV to PeV energies or so. Charged interaction produces a muon. This muon is very energetic, goes very fast. Its velocity is larger than the velocity of light in that medium, so it radiates Cherenkov light. This Cherenkov light is collected by photomultipliers, which are attached on strings, and these strings are, I mean, you cannot, we will see how large a detector for this type of, for collecting this type of fluxes should be, but you can anticipate that the fluxes are very low. These are neutrinos, so you need huge detectors, okay? These strings are deployed in natural media because you cannot really build a artificial detector, which is, we'll see, kilometer cube size, okay? So they are deployed in water or ice. In the case of IceCube, they are deployed in the deep ice of Antarctica. starting 1 kilometer deep and going up to, couple of kilometers deep. Antarctica ice shelf is very thick, actually. But you can do the same in water. There are examples in lake water. That's the case of Lake Baikal in Russia, or in the Mediterranean Sea. You have Antares and the ongoing efforts for the kilometer cube type of telescope in the Mediterranean, one in southern France, one in Sicily. These are a couple of sites. And I think there is another project at in Western Canada off Victoria Island. Okay. Anyway, these experiments, how can they detect? Okay, of course they can detect this type of Cherenkov light. If the particle is not a muon neutrino undergoing charge interaction, it can still detect a neutrino, say, of electron type or a tau type, because you can produce, for instance, in a charge interaction, you can produce an electron. It will still release light. It's just that the range over which it stops is much shorter. So for a muon neutrino, you will have a very long track, and in principle, it's so long that it can even be produced outside your detector and get out of your detector. So you will only see part of your track. For electron type of neutrinos or tau type of neutrinos, you have a more spheroidal type of energy release. So you must imagine that in this volume there are strings with photomultipliers, like a grid. And from the timing of the arrival of the light and from the total intensity of the light, you can basically reconstruct the trajectory and you can reconstruct the energy that has been released, or you have a proxy for the energy, rather the energy deposited. However, there are lots of stuff that can produce similar signals. In particular, you can have atmospheric muons produced by cosmic rays impinging on the top of the atmospheres. These are the same muons that in lecture 1 I told you about could be used to tell us something about the chemical composition of the cosmic rays. So if a muon is coming from here, and is being produced in the top of the atmosphere, how do you distinguish a neutrino muon from a cosmic ray muon? There are several tricks. One way is to put a surface detector on the top of your telescope, and so if this muon is coming from there, it will trigger a signal even on the surface, while this one won't. The same can happen even for a neutrino. A neutrino producing atmospheric events will not trigger a signal here, will, however, produce it here. So in order, a track, for instance, in order to reject these events, you cannot do with a veto. There is no way to veto a neutrino. So what people do is to compute what's the angular distribution of the flux and the energy distribution of this flux, and you look for something which has a different angular distribution and different energy distribution. Also, what you can do at low energies is to look only at stuff that comes from below, okay? So basically, you look from stuff that comes from the other side of the Earth. This filters out all the cosmic ray stuff. Of course, it cannot filter out the neutrinos. This does not work anymore if you go to PeV energies, because the Earth is opaque to neutrinos at PeV. So at PeV energies, you can only look at stuff that comes from the top. Okay, so energy spectrum distribution and angular type of distribution are crucial to separate these things. Okay, so these are a few experimental details. The announcement was made in 2012 that they had a few events of energies of PeV, and that were neutrino events in their detector, and as far as they could compute, they were orders of magnitude above the flux, residual flux that should be expected from atmospheric neutrino events in the background. So they thought they were extragalactic or whatever, astrophysical sources, neutrino events. And since then, they have been accumulating many type of events. They have collecting events at lower and lower energies. And by now, you know, they have many, many events from spanning from at least 10 TeV energy up to 10 PeV energy or so, with a spectrum roughly e to the minus 6, plus or minus 0.3, perhaps, something like that. They have detected muon neutrino, they have detected electron neutrinos, they have even detected tau neutrino. So it's a more complete picture. The point is that we don't know where these neutrinos come from. So, problem, where do they come from? Actually, do even they come from astrophysical sources? If yes, which type? Do we know about them? Are they new sources? Are they coming from exotic processes? Who knows, dark matter related maybe? So how do you do that? How do you tackle this problem? Okay, so today we will see, build up the type of tools that people have been using for addressing this question. The first thing I wanted to introduce to you is the process, the key process that in astrophysics is thought to produce neutrinos is pion production induced by protons or in principle nuclei. And we have already seen this yesterday, but basically the processes are P plus P into, let's say, I just write one, pi plus proton plus neutron. This is a possible process that produces neutrinos. How? Because then this pi plus will decay into mu plus a neutrino, and eventually this one also decays further into neutrinos. So you get a neutrino flux associated to this. I will use protons. Let's say this is a proton high energy with some target that is being produced. Whenever you have this process, typically you also have processes like pi 0, proton, proton. So you see a pattern here. This pi 0 is going to decay into gamma gamma. So whenever you think that there is a possible neutrino source, there should be an associated flux of gamma rays of hadronic origin. Maybe there is more, because maybe there are also electrons around, and maybe you have inverse Compton, maybe you have other stuff. But this is unavoidable. This is due to nuclear physics, hadronic physics, okay? Now, there are some, how many of these processes there are per each process of this type? Because we want to build a counting link between what to expect in neutrinos and what to expect in gamma rays. In general, if this process, this type of hadronic collision happen at very high energies, remember what I told you in the first lecture, you will have a multiple final states, multiple pions in the final states, so the real process is more like something like that. Some sort of n pions of different nature plus x. And this n is what I call the nu plus minus the multiplicity of pions in the first lecture. Okay, this can be 5, 6, things like that. So it can be a very large number if this guy is maybe PV, in principle. If, however, you are close to threshold, that's not the case. If you are close to threshold, so if these are many pions, statistically speaking, you have that the number of pi plus is roughly equal to the number of pi minuses and roughly equal to the number of pi zeros. And this is because you know that you have an isospin symmetry in strong interaction. So that's particle physics that tells you that. However, particle physics still deal with available energy, right? If you are very close to the threshold for some processes, these might not be true. For instance, let's think of the possibility to create a positive or negative charge pion in a PP reaction. This is more an academic exercise because the problem of this isospin violation is more typical for P gamma photopion production reaction, but it's easier for me to illustrate it in this case. Question, exercise. What's the minimum energy that you need to produce a positive a positive pion in a PP reaction. Naively, you can compute from here, you would say. And you would get a result which tells you that T of that, the kinetic energy of the threshold here, kinetic energy of the proton is about 292 MeV. This is not the minimum energy. The minimum energy is associated to this process, as you can realize quickly. Final state bound deuteron. And it's roughly 6 MeV lower. So this is, even with 286 MeV, you can still create a positive pion. If I now ask you, what's the minimum energy to create a negative pion, you still have to find a process where you conserve charge, you conserve the baryon number, etc., and you need things like this, pi plus, pi minus, proton-proton, for instance. And the kinetic energy at the threshold for this is more like, if I did my calculation correctly, is more like 600 MeV. Now, in very high energy cosmic ray sources, these are very low energies, right? So typically, you are always above the threshold. But this illustrates the fact that if you have some processes close to threshold, then you cannot really assume this type of isospin symmetry. In particular, processes which are going to photoproduction, like proton-proton into pi zero, proton-photon into pi zero proton, and proton-photon into pi plus neutron are roughly equiprobable, but processes that produce negative pions are very hard, because usually you would need the central mass energy of this guy to be well above, hundreds of MeV. And that's hard, because photon fluxes are strongly dependent. The photon background fluxes are strongly decreasing with energy. So just to wrap up this fact, this is a technical information that I will need later, but just to say that there is a link which is universal in the sense that it's always there between a mechanism of production of pions, which leads to neutrinos, and an associated mechanism, pi zero, producing photons. How much is this ratio? Depends on the actual process and can vary typically up to a factor 2, in the sense that if everything goes, isospin symmetry, you have roughly twice as many charged pions as you have neutral pions. But in this other case, you have as many neutral pions as you have charged pions. And this consideration can be made more specific to neutrinos and antineutrinos, or to neutrinos of different flavors, and so on and so forth. Okay? So these are the two informations you have to retain. The universal link between hadronic production of gamma and neutrinos, and the quantitative link which has a little bit of dependence. Now, let me tell you about some features of these spectra. What we can see at the Earth is not the pions that are produced at the sources. What we can see at the Earth are eventually these neutrino spectra and these photon spectra. Okay, so let me be a little bit more technically precise on what are the features of these spectra that we could expect. Okay, and let me start with the pion, neutral pion. Okay, so now my goal is to give you a link between the source term, in a certain sense, for the photons coming from pi zero, and the source term of the pi zero, which in turn is linked to the source term of the protons. That's what I want to show. And also, you might wonder, is there a way, for instance, to tag these photons as coming from protons rather than, say, electrons? And then we will see the same thing for neutrinos coming from pi plus or pi minuses. So maybe it's boring, but I want to show the kinematics in a simple case which is really telling you how people compute these things. So the pi 0 goes into gamma gamma. Okay? So in the frame of the pi 0, this is a monochromatic spectrum. It's back-to-back photons. And the energy of your photon in the frame of the pi 0 is going to be simply m pi over 2. As far, rather simple. However, this pi 0 is going to be produced in the lab frame. So it's boosted. And there is a typical velocity beta, which means that the energy of your gamma ray in the lab frame is given by the energy in the rest frame, m pi half, times the gamma, times 1 plus beta cosinus of theta, where this is describing the relative angle between the velocity and your photon. Okay? So what is the minimum and maximum energy that we would see in the lab frame? You have an E max min of the photon, which is going to be what? Pi half 1 plus or minus beta, because the minimum and maximum of this guy is going to be 1 minus beta or 1 plus beta. Also, we know that there is a one-to-one correspondence. It's a invertible function between the angle and basically the cosinus between -1 and 1 and the energy. Okay? So you basically have also the link that d gamma is going to be m pi half gamma beta d cosinus theta. The pi 0 is a scalar particle. Its decays are isotropic in the frame, in the rest frame of your pion. So the distribution of the photons normalized to 1 is going to be 1, the angular distribution of your photon, which means if I integrate now over the azimuthal angle, the phi, not the theta, you get that dn is directly linked to d cosinus theta. Okay. So all these trivial things I'm just using to say that if you want to know the differential number of photons normalized to 1 with respect to energy, this is simply given by 1. You have basically the dn here with respect to cosinus theta and the d there with respect to cosinus theta. They are both one-to-one relation. So you take the ratio, dn over d is 1m pion gamma beta. This is also given by basically, this is the energy of the pion, gamma times m, energy of the pion in the lab times beta, which you can also write as 1 over square root of m pion square minus, sorry, e square pion square minus m pion square. This is a flat distribution in energy space between the minimum and maximum energy. And in particular, in the relativistic limit, you see that the minimum energy of your photon is going to be 0, and the maximum energy of your photon is going to be m pi. Okay? So our spectrum of the photons in the lab frame, in the intrinsic frame, this is the energy, and this is the number, you get a delta, which is at m pi half. In the lab frame, in the relativistic limit, you would get something like that, which is symmetric around the half mass of the pion. In particular, you can compute, this is what people tend to do, because people in astrophysics tend to plot these things in a log space, in log plots. The average of the log E min and log E max of these photons is going to be given by the log m pi alpha. Now, whatever is the distribution of the initial energy, of course, the width of this guy depends on the energy of my photon, or my pion, okay? If you wish, on the velocity beta of my pion. However, no matter which beta, it's always going to be like that. It's always going to be symmetric around this half mass. So, whatever the spectrum of the pion, okay, it's a different beta, you will get something like that. Or maybe much larger, depending if it's relativistic, non-relativistic. But the fact that it's always centered around this is a signature. In principle, if I can measure very well the spectrum, and I find that my spectrum is symmetric around this, because you must now sum all these unknown contributions, but still they will be symmetric. If it's symmetric around alpha of the mass of the pion by 0, which is 67.5 MeV, then I have a smoking gun for the fact that these are of hadronic origin, okay, which is an unsolved problem in a certain sense. It's very hard to find this signature. There are a few papers that claim that they have seen this feature in some spectra. Yes, it's there, but it's very hard, and this is an experimental problem, essentially, in the sense that it's much harder to measure gamma rays at tens of MeV than it is to measure gamma rays at GeV, because the techniques for detections change dramatically. At high energy, you typically use the pair production technique for detecting the photon, which works very well. For lower energies, you need to use other techniques like basically Compton scattering, and that's much more challenging. So we know much better the gamma ray sky at GeV energies than we know the gamma ray sky at 10 MeV energy, okay? But in principle, this is one goal that we had. Can we identify gamma rays through this, produced through this mechanism? The answer is yes, at least in principle. How do you compute what I promised you? So the link of the source spectra in gamma rays given some proton spectrum. Well, the pion energy is related to the proton energy by through the inelasticity of your process, and within some limits, but for the analytical results I want to obtain, let me write this approximation. The energy of the pion is a fixed fraction of the energy of the proton that produces it. Okay, this is not true. This is a slightly evolving function of energy, but okay, let's keep it. And roughly this guy has a value of 0.15 to 0.2. That's just to give you an idea. In general, that's not true, so you would need the differential cross-section of a proton in the pp into pi production of producing a pion of energy E pi given a proton of energy EP. Okay, that's what you need in a complete case. If I do this approximation, this differential cross-section, I can write like the total cross-section sigma pp into pion production, function of the energy of my proton, times a delta of the energy of the pion being fraction kp of the energy of the proton. Otherwise, you need the more complete expression. So the first step, the pion source term as a function of energy of the pion is related to the proton parent spectrum that produces it by this approximation. E proton times this total cross-section that depends on E proton times the flux of E protons times, in principle, whatever target density. Let's put it here. In this simple process, we consider just hydrogen target. In general, you have to sum this guy over all possible targets of your interstellar medium. Under the approximation there, you can integrate this, and this is density of hydrogen over k pi times this cross-section evaluated over E pi over k pi times the flux in E pi over k pi. Otherwise, you have to perform numerically the integral. Okay? So once I have a flux of protons, I have my target, I have the cross-section, I can compute the spectrum at the source for the pions. First step. Second step, once I have the pion spectrum, how do I compute the photon spectrum? Well, we know all the key information. Let's plug them together in the formula. Okay. This is going to be the integral over all the pi spectra. I'm basically doing analytically what I was describing here in a little cartoon, times the differential number of photons produced with respect to the energy times the spectrum of the pions. And since I chose to normalize my number of photons to 1, I have to multiply by 2, because there are 2 photons emitted in the decay. Over which energies do I integrate? Well, in principle, up to infinity, or whatever high energy my pion spectrum dies off. And I have to integrate from which energy? From basically the minimum energy of a pion associated to the energy of a photon E gamma. And this thing, let me write the result, and I tell you where it comes from. This is equal to E gamma plus mass of a pion square over 4 E gamma. And this result comes from the fact that, we have that E gamma min times E gamma max is equal to m pi square over 4, and also that E gamma max plus E gamma min must be equal to E pion. So for a given energy E pion, the maximum energy of the photons you can write as E pion minus E gamma min. And you can solve for E pion by inversion, and you get that relation. Okay? It's a little exercise, should be simple. So in principle, we have solved what I told you was my goal. I want to find the feature in the photon spectrum produced through hadronic production, and I want to link this to the pion and thus the proton spectrum. So I have everything now, right? In that integral, I can replace the source term for pions, which I can write this way, and that's it. In the limit where this cross-section has a very small dependence from the energy, you see that this, imagine that the proton spectrum as a, this is the flux of proton, as a power law shape. The source term for pions will have the same spectral shape as the proton that I've produced them, and eventually even the photons. Okay. We can repeat basically the same thing for the neutrinos. The neutrinos produced, let me just limit myself to the case where you have the pion going into muon plus neutrino, and let's discuss the distribution of energy of these neutrinos. Of course, there will be other neutrinos coming from the decay of muons, but then it becomes, you can do even analytically, but it becomes cumbersome because you have to to have multiple integrals in your calculation. So again, what's the difference with respect to the case previously done? The only technical difference is that this particle is massive, so this energy won't be the half of the energy of your pion. But apart from that, it's again a two-body decay, and things are relatively straightforward. So just for the sake of completeness, let me write down what is the energy of the neutrino first in the frame of the pi that is decaying. Okay, I will use the fact that the p pi minus p mu square must be equal to the p. No, let's write it this way. P mu square. And from this, I deduce that E nu in the frame of the pion, which is decaying, is going to be m pion square minus m muon square over twice the pion mass. And this is about 29.8 MeV. However, this is moving at some velocity beta. So the energy of neutrino in my lab frame is going to be nu star in the rest frame times gamma. That's exactly the same story we saw before. We can deduce that, it's writing less and less well, E nu max in the lab frame now is going to be given by mu minus mass of the muon over twice the mass of the pion times gamma 1 plus beta. This gives you mass of the pion square minus mass of the muon square over twice the mass of the pion times twice gamma in the ultra-relativistic limit. And this you can write simply, you multiply and divide by m pion. This becomes the energy of the pion. And here you can simplify, that goes away of course, and you can simplify. And this gives you a constant, which is 1 minus mass of the pion, of the muon square over mass of the pion square times the energy of the pion. This is valid in the ultra-relativistic limit. And this constant, which we can denote lambda, E pion, is about 0.43. Not very deep, frankly, but I really wanted to show you in practice how these things are done. And then we can proceed as before. The source term of neutrino energies given by the integral of the minimum pion mass associated to the energy in nu up to infinity integrated over all pion energies dn over dE times Q of E pion. Now this is the source term of the charged pions, of course. We use that relation and we rewrite this as essentially in the relativistic limit. This is E nu over lambda to infinity dE pion Q E pion over lambda E pion. And we see that basically, if this is a power law, the neutrino has the same power law of the parent-pion spectrum. Concerning the number distribution, we can repeat exactly the same argument as before. dE nu is basically E nu star beta gamma d cos theta, and we know that dN over d E is going to be equal to 1 to E nu star gamma beta, which is also 1 over lambda e pi. That's what I used here. Huh? That's exactly the step that we did before. And again, you can go on, compute the same way the differential energy spectrum of the muon, then you make your muon decay, and you will have differential energy spectra in the frame of the muon, and then you convolute the differential energy spectrum of the electrons in the frame of the muon times the distribution of energy of the muon in the frame of the pion times the distribution of the pion, etc., etc. So these are just integrals that you have to do. So there is nothing deeper than that. But there are a few things that you can expect, of course, in the process pion going into muon neutrino plus going into electrons, neutrino, antineutrino. Okay, there will be at least one antineutrino, maybe two, depending on the sign. There are 4 particles in this final state. Roughly, the average energy of one of these 4 particles, in particular the average energy of my neutrino, will be about 1/4 of the average energy of my pion. Instead, for my photons, I expect that the average energy of my photon, well, that's exact, but it's basically E pion half. So the average energy of a neutrino is going to be half of the average energy of a photon associated to the same type of processes. Concerning energy, total energy, not energy of a single particle, but total energy available in the photon and neutrino channel, what can we say? Well, what we can say is that let's first consider the case where the number of pi plus is equal to the number of pi 0. This happens, for instance, near threshold, and it's typical for photoproduction of pions, not hadronic production of pion, okay? In this case, the total energy into these and these are the same. However, this energy is all channeled into photons, while only 3/4 of this energy are channeled into neutrinos, okay? So if we want now, there is a link which is the total energy carried by the photons. Let's write in a more technically correct way. This link is between the energy of the photons times the differential spectrum of the photons with respect to the... I use epsilon because now I'm referring to the energy at the source. Later, after a break, I will show you how this translates into a flux integrated over a redshift, okay? So epsilon for me, from now on, will be the energy at the emission time, not at the Earth, just to be. So this is going to be, in this case, 4/3, because this one is 3/4 of this one. So this one is 4/3 of the other one, of the same quantity, evaluated, however, at the energy of the neutrino, which is half of the energy of the photon. I just want you to understand where this comes from. It just comes from the energy budget in the parent pions and the average energy that the photons and the neutrinos have in the decay chain, okay? If you have isospin symmetry, they are all equal, then there is twice as much energy into neutrinos than in this calculation, which means half that much energy into photons. So this is typically taken into account via a factor K, or kappa in general, it's denoted. This kappa can be 1 in case of maximal isospin violation, or 2 in case of no isospin violation at all, okay? Concept is, we know how to compute the spectra of neutrinos once we have the parent proton spectrum. we know how to compute the spectra of hadronic photons once we have the proton spectrum. They, by the way, have roughly the same spectral shape of the parent proton distribution, and they are linked. Okay, for the photons, we have even a signatures that should tag the hadronic origin, and they are linked in this way within a factor 2, basically, depending on the exact production channels. Okay? So we have now all the ingredients to show you where the puzzle in the ice cube interpretation comes from. But since I have no more lecture, so I cannot tease you for the following lecture, I tease you for the following half of the lecture, and now we take a break. Okay? So here we are, final steps. So a comment about one fact that maybe it's not obvious to you, but let me tell explicitly, is that when ice cube sees something, we have no idea where this neutrino is coming from, right? One reason is that the horizon for neutrino interaction is basically infinite. So it's of cosmological nature, to be more correct. So we are basically, with neutrino telescopes, we are going to collect from the whole universe and from the whole history of the universe, at least up to CMB formation time or so, in principle. Basically, up to the formation of the first objects, like first stars or first massive black holes, etc. So in order to analyze, to parameterize the problem, let me do some simplifications which are not strictly necessary, but help in the description. So let's introduce some neutrino spectrum, which is unknown, of course, in principle, of a single source, dn over d in u. This is the spectrum of the neutrinos at the source. It depends, of course, on the... This is really... this depends on the neutrino energy, and in principle can depend on redshift, explicitly. What does it mean explicitly? Imagine that you have one class of sources. That's our mental picture. We have one class of sources which is responsible for this neutrino source. This class of sources might have its properties, like the spectral index or the maximum energy, function of the cosmological evolution. Imagine that this is coming from supermassive black holes. Imagine that there is a link between the energy, maximum energy of acceleration and the mass of this supermassive black hole. And imagine that this supermassive black hole grow in mass with time. Okay? In that case, you would expect that there is an explicit dependence on redshift. I will ignore it in the following. You can do the general problem if you want, but I will assume that these guys are simply dependent on energy, which means that these are sort of standard candles. This population of objects is always the same at any redshift. Which also means, in practice, that if I compute... So this is typically in units for experimental studies, this will be the number of neutrinos per unit energy, per unit second, per unit surface, per unit solid angle, things like that. So you may have, or maybe, the number of neutrinos per second per unit energy, depending on the application, okay? So if I use this second convention, then the luminosity, intrinsic luminosity associated to a source, L nu, will be simply given by the integral over d epsilon nu of epsilon nu times dn over d epsilon nu from a minimum and a maximum. And what I'm saying by saying that these are standard candles is this is a constant. This luminosity of a given neutrino source is a constant. Again, this is just a simplifying assumption, it's not needed, but it helps. So my question is, what's the flux at the Earth of neutrinos? Now, let's say, for the sake of the argument, we want to know how many neutrinos you detect at the Earth per unit time, per unit solid angle, per unit surface, per unit energy. dE. I use capital E for the energy at the Earth. So, yes? No, okay, it depends on Z, because what you see at the Earth, so the link is that epsilon nu is 1 plus Z times the energy that you see at the Earth. Now, I'm putting these sources at different distances from us. So even if intrinsically they are all the same, the energy that I see coming from a source near close is the same as the source, as the intrinsic energy. For a source that is very far away, this will be much degraded in energy by a factor 1 plus Z. Okay? That's what I call implicit dependence on redshift. Huh? Now, the differential flux of neutrinos can be computed. This is now per unit solid angle, so I put a 1 over 4 pi. Huh? I have to integrate over the whole volume. What? The density of these sources. I put a little c for saying, because I'm working co-moving units. If you know cosmology, you know what I'm talking about. If not, consider the classical case. This is just the volume. And the density of sources per co-moving volume, I denote with a curly f. This is the typical symbol used in the literature. Then per unit surface, so I have to divide by 4 pi d co-moving square. Huh? D is the distance, so I am normalizing to the source up to dc. And then I have the dn over the dE, sorry, over the dE epsilon, but computed in 1 plus z times E nu. And this is now the energy that I see at the Earth in ice cube, say. Okay? What is this VC? Okay, VC co-moving volume is going to be 4/3 pi d co-moving cube. I can write dVC with respect to Z as dVC with respect to dC times ddC with respect to Z. This gives me 4 pi dC square, and this is going to give me a 1 over Hubble factor, basically. Huh? Again, if you're familiar with Friedman, Remet, Robertson, Walker type of calculation, this is trivial. Otherwise, just trust me. So that quantity, this is really bad. Let me write it this way. The flux with respect to energy per unit solid angle per unit surface is going to be 1 over 4 pi integral over dz f of z over h of z times dn over dE 1 plus z times E nu. For instance, the integral dz dvc over dz times f curly of z, this is the total number of sources that are contributing to my neutrino flux. What IceCube measures is basically that type of integral. In particular, one quantity that we can derive from IceCube flux measurements is the total power detected in my detector. So basically, it's going to be the integral over the energy times the dN over dE. So, the d phi over d. The d phi, it's impossible, over d phi. Okay? Now, I introduce my variable y, which is 1 plus z times E, and I want to change variable to y. and I take the expression for d phi over dE that I've derived, and I get dy y over 4 pi times dN over d epsilon times, as a function of y, times an integral, which is now an integral just over redshift of f of z over h of z. Let me erase this, which we don't need anymore. Okay. So this power, think of it like the quantity that can be easily measured by ice cube, is going to be given by L nu. Remember, I can reformulate these in terms of L nu. This is the energy times the number of neutrinos, times, let's write it like F0 over 4 pi h naught, and then I can write psi zeta, and this psi zeta is a number which depends on the redshift distribution, not on zeta. It's integrated over zeta, and this is nothing but dz1 plus z square f z over f0 h naught over hz. So it's a dimensionless quantity. It's of order 1. In general, it depends exactly on what you give for your distribution of sources in redshift, which is unknown. So this is basically parameterizing our ignorance on how these neutrino sources are distributed in redshift. And you see also that this quantity that we measure is fully degenerate between the luminosity of a single neutrino source and the density of neutrino sources. Okay, so if we measure an isotropic source, an isotropic flux, we have no idea if this is coming from a few powerful sources or a lot of dim sources. These two things are indistinguishable if we just have the average flux. In order to distinguish them, you have to look for instance, for clustering. If I'm convinced that multiple neutrinos come from a single source, then I can break this degeneracy. And I can measure separately the luminosity and the density. Okay. Now, using the relations that I wrote before between neutrino energy and photon, hadronic photon energy, I'm wondering, can I relate this thing that I have measured at ice cube with the analogous quantity for photons? Now, in principle, yes, if I limit myself to the photons emitted at the source, because neutrinos are only subject to redshift. Photons, however, will be reprocessed in the sense that I told you yesterday that the horizon for photon propagation at PV, TV, PV energies is very short. It's not cosmological. Okay? So photons, although, remember there was this relation epsilon gamma dn d epsilon gamma equal 4 over 3 kappa epsilon nu dn over d epsilon nu evaluated in epsilon nu at half of epsilon gamma. This is true. Here it's basically I know everything, but here this thing is evolving over redshift because now they are getting absorbed. So what happens to these photons? Because if I cannot find an origin for ice cube neutrinos, maybe photons are helping me. Now, the simplest thing would be you see a neutrino and you see the gamma ray from the same source. You see another neutrino and you see a gamma ray from the same source. This cannot happen, I told you, because these photons are going to be absorbed. So I have to find a relation which is between whatever happens to these absorbed photons and the neutrinos. It can happen if some of these sources are really close by. And there are some claims that maybe one or two events have a counterpart in gamma rays, but there is a time delay, people are debating. Certainly there is not a single population that seems to correlate. People have looked for correlation for the arrival direction of these neutrinos with gamma ray burst or blazars, and nothing seems to work out very, very well, actually. We have upper limit. None of these classes seems to be contributing more maybe than 10% to what the total number of events. So is there another more bolometric way to gain insight on that? And fortunately there is. Fortunately there is, because once I have my energetic gamma, I told you what happens to an energetic gamma, which is TV to, in particular, PV energies, because IceCube has detected photons up to the PV, 10 PV. Typically, this will pair produce. If it's PV, it can produce on the CMB, but even if it's, 10 TeV or so, it pair produce on the extragalactic background light. As a result, you get E plus, E minus. Each one of these can do inverse Compton onto the CMB, and so for each one of these, we'll actually do E plus gamma CMB into E prime plus gamma. And this guy has an energy roughly gamma square, Lorentz factor of this guy, times the energy of the CMB. If this new energy is still above the threshold for pair producing, this goes on. And this is an analogous, a cosmological analogous of the process of a shower development in the atmosphere. Remember our friend Eitler? A multiplicative type of shower. But this is now happening over gigaparsec scale, not in our atmosphere. At the end of the day, as in the Eitler model, these photons will be incapable of pair producing once they are degraded below some threshold. When does this happen? Well, I told you what's the threshold for this to happen. It's typically TeV scale, right? So at hundreds of GeV, photons will fall below this threshold. So if we integrate the whole energy of diffuse photons, because now they will have lost track of direction, they will arrive from everywhere, because in these cascades, right, this photon does not have the same direction of this one. If we integrate the total flux of photons below 100 GeV or TeV energies, this total flux should be equal to our integral of the neutrino flux, modulo this conversion factor, 4/3 over K. Okay? So I don't find a direct correlation. I know that it can be hard, because I should find a direct correlation with gamma ray sources only for the nearby universe. I can look at the total number of fluxes collected by an experiment like Fermi at energies below the TeV. And the total energy stored there should equate, if it's all hadronic, should equate the neutrino energy. That's the argument. Now, to be more precise, I can also compute actually the spectrum of these. So this cascade is amenable to an analytical, semi-analytical calculation actually done by Berezinski and collaborators. So if you are curious, in the notes I give you also the spectrum that is associated to these multiplicative cascades at the Earth, if these cascades has the time to develop fully. If the sources are so far away that you really process photons down to the level where they cannot pair produce anymore. If this is the case, the spectrum of the photons that you get, let's use n gamma to avoid confusion with phi of neutrinos, of E gamma. This, if you are curious, this has a sort of broken power law shape. So it's proportional to the energy to the -3 half in some range, proportional to E energy of -2 above, and it's 0 still above. Which energy range? It's 0 above threshold. So when energy is larger than me square over epsilon EBL, which is about 0.4 TeV. It's e to the minus 2 in between these 0.4 TeV and something which is about 0.1 GeV, and it's e to the minus 3 half, and this comes from the requirement that this is not multiplicating anymore. And you find the analytical expression if you wish, and it's e to the minus 3 half below. So actually we know how this spectrum should look in this universal limit. This is an extra information. If you are dealing with actual distribution of sources candidate, I mean, like in some recent paper, for instance, of our group, you want to go beyond that, right? Because some of these photons might be sourced at distances which do not allow the full computational, the full development of this shower. But okay, that's a first approximation. You don't really need to know. By the way, you can also, it's not just the proportionality. You can predict also the normalization, and it's universal. It only depends on how much energy you inject into photons, okay? Which means that modulo factor 2, I know even the normalization of this guy. And basically, I would expect something like a relation of this sort. P gamma hadronic, based on this, should be 4 over 3 kappa of P nu of ice cube. Okay? The only hypothesis that enters this relation is that there is no leakage out of the photon into some other particles. Now, if I take Fermi measurements, these have measured the diffuse gamma ray flux below the TeV. So the story is just that there is a flux that has been measured in gamma rays. So in E square d phi gamma, d phi over dE, sorry, d phi over dE, this is something like that, I don't know. This is the flux measured by Fermi. Roughly, this could be TeV, and this is maybe 0.1 GeV. That's the range of sensitivity. And here I have, if you want on the same plot, I can plot the flux measured by ice cube in neutrinos. And essentially, this thing is constraining me. Now, this thing is contributed by anything. Is contributed, for instance, by population of gamma ray sources that we know about. But also should be contributed by these cascades. So the relation I should find, in principle, is that P gamma associated to ice cube plus, or better, P gamma of all cascades plus P gamma of known stuff should be larger than P neutrino. And it turns out that that's not what we find. If you do that, you find something that is rather like that. So it seems like there is less energy available in the isotropic gamma ray sky than the minimum energy that you would expect to associate to counterparts of neutrinos. Where is the wrong ingredient in all that? Where is the weak point in the argument? Now, according to some people, the weak argument is here. We make something wrong when we extrapolate from what we know of the known gamma ray sources into the overall unresolved contribution that these gamma ray sources should provide to the Earth. Okay, this was, personally I believe this was possible and credible early on. It's becoming less and less likely to me now because we have a lot of constraints on this understanding. For instance, we can make prediction on the anisotropy pattern of this background based on the spectrum if we interpret them correctly in terms of a mixture of objects like blazars plus starburst galaxies, etc., etc. And this prediction agrees. It seems like a coincidence. So we have some sort of resolved object. We say, okay, this is the tip of the iceberg. There should be some unresolved counterpart of these resolved ones. We can compute their spectra. The spectrum agrees. Then we can compute the anisotropy pattern expected to that, or pixel statistics, other things. And this agrees with what we see. And still, this argument seems to fail. Okay, it could still be that something gets wrong, but to me, it becomes less and less credible. What else could be wrong? One thing that could be wrong is that Fermi only measures down to 0.1 GeV. Now, this is okay in a certain sense, in the sense that for typical sources, this flux has the bulk of it in that range. However, imagine that there is a process where the energies of the photons is degraded below that. If this is the case, then this argument can be evaded. For instance, people have thought of what now they are called choked sources, or sort of opaque sources. So imagine that you produce photons and neutrinos, but somehow the photons never get out energetically from the source. For instance, they thermalize in the source, or they get degraded to MeV energies. That's enough, because then you can evade this argument. That would mean that IceCube has seen a new class of objects, which we don't know about, basically. Examples could be failed supernovae, failed gamma ray burst, something where the shock starts being produced. Remember what I told you about that. In this shock, you can accelerate, for instance, protons, produce pions, the neutrinos get out, but then it's opaque enough for the photons to be absorbed, maybe thermalized, and then maybe a black hole forms. This would be an example of a source that evades this argument. Another thing that could happen is that our assumption that these objects are cosmologically distant is wrong. However, IceCube detects a flux which is basically isotropic, consistent with isotropic, maybe slightly enhanced toward the galactic center. So, if it's not cosmological, then maybe there is some new physics involved. Dark matter decay would predict some type of distribution of this sort. If it's not cosmological, then you might arrange for something. Of course, you should have a cosmological counterpart of the dark matter signal. So still a weaker version of this argument applies, but you gain a factor 3, and that's more than enough to reconcile the tension. If this is the case, then you will have both neutrinos and gamma rays. But if this is the case and these are galactic, then remember the mean free path for a PV photon is 10 kiloparsec. So if this is the case, we should have Pevatron type of gamma ray emission from the halo of our galaxy. This is a prediction of this model. And there are experiments running, Tibet AS, LASSO, that are sensitive at hundreds of TeV. And now they have started to release some data, and these data seem to put constraints on at least part of already these models of dark matter. Okay, not all channels, not all possible particle aspects, but some of these are constrained. So you start seeing the link between IceCube, Fermi, ground-based gamma ray detectors. How do you test all these things? Of course, we don't know what the answer is, so I'm not going to give you any revelation. But you can also use this type of information to do, for instance, searches for new physics or constraints to new physics. Once for instance, the first time IceCube detected neutrinos to PeV energies, one thing that you can be sure of is that these PeV neutrinos must be able to reach us from whatever cosmological distance they come from. If Lorentz invariance is violated at high boost factors, and a neutrino of a PV has a very high boost factor, something like 10 to the 16, something you have never tested before. In principle, if they violate Lorentz invariance, there are some models of quantum gravity where their velocity should be different from what you naively expect. So neutrinos propagating in vacuum at these high energies would behave like the muons I was talking before. So like having a velocity larger than the speed, the velocity of the light in that medium. So they should do sort of Cherenkov type of emission. And that would degrade their energy. From imposing that this does not happen, because we see them. And by the way, neutrinos would degrade their energy. This is an argument that was also used to constrain explanation of the transluminal neutrinos in opera, if you have ever heard about that. So neutrinos, by Glashow in particular, so neutrinos should Cherenkov radiate. Of course, this is an electroweak type of radiation. So, for instance, you have processes like this. Because for them, the empty space becomes a medium at this high, in this type of models. So you have injection of electromagnetic stuff. These guys will start doing inverse Compton, blah, blah, blah again, and contribute to the flux I was showing before. So from comparing what you see here and what you see here, you can set an upper limit to how many of these events are possible. And this you can translate into a limit of the scale of quantum gravity models that predict this event to happen. Okay? Once we did this, I don't know, there is a reference, I think 2013 or 14. These were the most stringent bounds on the violation of Lorentz invariance in the neutrino sector available. Okay? So this is just to say that you have a new window that is being opened. IceCube has detected this flux. You don't know where it comes from. You start using the tools that you have, our knowledge of gamma ray sky, our knowledge of the link between protons, neutrinos, and gamma rays, to try to figure it out. You have some puzzling result. It doesn't seem to be clear what are the counterparts of these neutrinos. Still, this does not prevent you to raise some hypotheses, both of astrophysical nature or of new physics nature. And in turn, these hypotheses allow you either to put constraint on theory of quantum gravity or to have prediction for dark matter that are now being tested. And that's a typical example of what we call multi-messenger astronomy. And more in general, in this case, since new physics is involved, you have astroparticle physics with multi-messenger tools. Okay? So it's just one example I cooked up from the many that are being used in the literature. There are some exercises that are, proposing you to compute quantitatively these things that I was talking about with a reference to the literature, so you can go look at these papers and redo the calculations. And I hope for those of you who are entering this field, my understanding is that only few of you are actually work in this field. This is a gentle introduction, a sort of adiabatic transition from learning literature and hands-on type of projects. For the others that are only exposed to this once in their lifetime, I hope now we understand a little bit better what these crazy people at the interface of astrophysics and particle physics are doing. And hopefully when you read the archive or some popular science, you have a much clearer idea. Okay, so I'm stopping here. I take maybe questions if you have questions on the course, on this lecture, or more broadly on the field. Maybe also online, I can check. And otherwise, we can say goodbye. Okay? Yes. Yes. So essentially, there are quantum gravity models where you change the dispersion relation. Okay? If you change the dispersion relation, you can change the velocity that you expect for different type of particles in propagating. This thing is, however, this is only happening as a function of the energy of your particle in your laboratory. So these are things that you need high energies in your frame to shed light on. Because by construction, Lorentz invariance must be valid at the energies where we have tested it. So in these models, I mean, if you want more details, I really address you to the literature, otherwise this becomes a quantum gravity type. But the idea is that in these models, when the velocity of your neutrino is very high, or the energy of your neutrino is very high, de facto, it's like it's propagating superluminally in the medium. The medium being the vacuum, in this case. You know what happens in the standard case where this happens. You have Cherenkov type of radiation. Of course, the neutrino is not interacting electromagnetically, right? So you don't have processes like muon into muon plus gamma. At least not mediated electromagnetically. You also have neutrino. You also have actually neutrino into neutrino plus gamma, and this has basically no threshold. And the particle physics origin of this is different, however. So in one case, you have neutrino. You can have Z-Strahlung, virtual Z-Strahlung. Sorry, this is one diagram contributed to this. But you can also have diagrams. This is a W, this is for instance, an electron, if this is an electron neutrino, and then you can attach the photon, for instance, here or here. Okay, so you can have also this diagram. This is all, I mean, these are diagrams that you can use to compute these processes of this type. The new physics part of it is that this happen in vacuum. This is not predicted by the standard model, of course. And once you have injected this energy, a cascade will develop according to what we have said. Now we are talking, these neutrinos are PeV-ish neutrinos, so these electrons are maybe hundreds of TeV, so plenty of energy to start a cascade and drain energy into the photon diffuse background. Okay, so we can repeat the same argument. We can measure, you know, imagine that this process only happens once. If it only happens once, it means basically that you should have comparable energy in the final neutrino and the electromagnetic part. So if I take the ratio of this thing to this thing, and this is 1, I can say in the worst case, this process can only have happened once over gigaparsec distances. So this tells me the strength of this violation of Lorentz invariance, maximally allowed. If this ratio is 100, okay, you get the idea. So that's how you proceed logically. More questions? By the way, one thing that I didn't tell you. At the end of the past century, people use similar arguments involving ultra-energy cosmic rays to estimate what's the size of neutrino telescopes that could detect a few events per year. Okay, one of these famous bounds is it's a bound is known as Waxman-Bachol bound. So the idea was the following: we know that ultra-energy cosmic rays above 10 to 19 electron volt are extragalactic. We know. There are good arguments. Some of these I presented to you. The fact that, and one was an exercise, the fact that these look isotropic. Another argument was the Hillas criterion, right? The fact that there doesn't seem to exist in the galaxy environments which can confine particles at these energies, and so on and so forth. So there are a number of arguments that suggest strongly that ultra-energy cosmic rays at these energies are extragalactic. If this is the case, you can take the flux of protons, or according to your assumption, protons, iron, or whatever, above this energy, and compute the pion flux that should be produced when these guys propagate in the intergalactic material, hitting the CMB. Okay? These are called cosmogenic neutrinos. This is one scenario. Huh? And this calculation was done for the first time by Berezinski and collaborators. And so you can link a sort of minimum flux of neutrinos that you expect to be there with the observed flux of ultra-energy cosmic rays. Another example of multi-messenger type of links. Of course, you can gauge what's the typical size of a telescope that should be able to detect, this flux. Now, this is not applying very well to IceCube because, for energy matching conditions, but this gives you a flux level. And this flux level is roughly the flux level that leads to a few events per year in a kilometer cube type of telescope. And there were many versions of these arguments for more or less stringent hypotheses, linking them rather to the sources of these ultra-energy cosmic rays or to this propagation, okay? But they were motivating the benchmark size of experiments that should see something. Now, is it a coincidence or not? Once we managed to build the first working neutrino telescope of a kilometer cube size, we got a detection. So some people still argue that this was a lucky coincidence, but there are many arguments. You can do the same arguments with galactic sources, etc., and you roughly end always in the ballpark of the kilometer cube. So again, multi-messenger type of approach could help you design an experiment to make a discovery. Now, this discovery is stimulating links and maybe puzzles and maybe new searches in astroparticle, etc. That's how this field works. It's a field which is extremely discovery-driven. It's rarely the case that some theorists think, oh, what could happen here? No, we are spending most of our time trying to understand what we see, not what we hope should exist in nature. So it's a little bit like maybe particle physics in, I don't know, the 60s, or when people saw lots of things that they didn't understand very well what was going on. Okay? More questions? If not, you can always drop me a line, an email, or